Good morning, everyone. My name is Eddie Rusu. I study applied and computational mathematical science at the University of Washington in Seattle, and the title of my project is EigenForests. It is a classification of kelp forests in the Santa Barbara Channel through image processing techniques. The motivation behind this project is that we have such a big data set of images. Just with the NASA Sarp flights alone from 2010 through 2014, we have 12 different flights that show kelp in the Santa Barbara Channel, and in each flight we can use the first 10 bands to look at kelp. And so we've got this data set of about 120 images. And so my project is to use image processing techniques and some statistics to see if we can look at the data set and pull out some of the spatial characteristics of the kelp forests, and to see if we can do some classification between kelp forests and clouds or whatever might come up. So we start by georeferencing our data. If you fly in the master, if you fly with master taken images, this is what master sees right here. But what we would actually see if we were up there with our eyes is a georeferenced image. And so we need to georeference all the images. And then I have to align them. So I go through and just line up all the images. And you'll notice that every single image takes a different section of the Santa Barbara Channel. And so I only consider the intersection of all of the images. So just the area in the channel that all the images cover. And I crop out that area. So you can see it's not quite as big as the entire channel, but it is good because we do see kelp forests here. Especially the Isla Vista kelp forest, which is one that is very often studied. Then I mask out the land to bring our attention just to the ocean. And if you see, as I kind of go through these, we can see sort of the general shape of what that kelp takes. A little bit of variability here and there, but for the most part, it looks the same. The last thing that we do before we're ready to go forward is to remove the variability from the shoreline. And so we do that using a puppet warp transform in Photoshop that actually takes the shoreline and just flattens it. And that way, when we have that flat shoreline, we can actually just remove those pixels from our image. And that looks like this. So it's really good. You can look at these images and say, oh, I see kelp in these images. But more than just, oh, I see kelp, I see what kelp generally looks like. If you look through these images, it's not changing a whole lot. There are a little bit of variability here and there, but for the most part, it's pretty consistent, which shows good promise. It shows us that we should be able to get a good idea of what kelp looks like in the Santa Barbara Channel. So with that, I'm going to go ahead and start explaining my algorithm, which I wrote in MATLAB. Basically, initial setup is just to clear everything out, set up some image dimensions, and set up some storage for the images that I'm going to be loading, which I do here. It loops through all of the different flights, and it only looks at bands 3 and 6. And the reason we only do that is because we're using a marine vegetation index that was actually found by James Allen 2 years ago in Sarp. And it uses a division of, or quotient of 2 different wavelengths, and the closest we can get to those wavelengths in master are by using bands 3 and 6. So then I go through that, I convert all the images to black and white, I shave off the top 3 pixels like I talked about. We want to get rid of the shoreline. Then I reshape the images and I store them into the appropriate matrix. And the reshape algorithm, the reshape function is really cool, because imagine that you are looking at 4 different images which are represented by 4 different matrices. And when you call the reshape function, it takes the columns of those images and stacks them vertically. So now you have one matrix to look at 4 different images, or 10 different images, or 120 different images, or however many you have. The next thing I do is calculate the marine vegetation indices. And so again, it's just band 6 divided by band 3. So here you see, for one flight, you see band 6. Below that, you see band 3. And when we do that division, we get this. And so you can see from this image, the kelp is really brilliant. It's really lighting up. Our focus is immediately drawn to the kelp, which is good. It shows promise there. What I've done, I did that to all of the different flights, and I've scaled it a little bit differently so the ocean is darker, so we can see some of the gradient of the light within the kelp. Then I took the average of these MVIs. So again, we're looking for what is the characteristic shape of the kelp. Well, let's find the average to see what that looks like. And here it is. Very promising, dark ocean, bright kelp. We can see kelp that looks really good. But as most of you probably know, it's not good enough to just get what something is on average, because things aren't consistent, throughout a time series, or things change. And so we want not only the average, but we also want the primary modes of variation. So we're going to find those modes by doing a principal component analysis. We start by subtracting away the average from all of our data, which will allow us to focus on the variations or the distinguishing characteristics within our data set. I do that with a singular value decomposition, and the best way to mathematically understand what this does is to consider a circle in a two-dimensional space that's being acted upon by some transformation or some matrix A, and this is what we get as our output. Well, the singular value decomposition takes that transformation A and breaks it into a rotation, a scaling, and then another rotation. So how that looks like for our data set is we have a matrix A of all those reshaped images that gets decomposed into a unitary matrix U, which stores the variations from the average, a diagonal matrix S, which stores the strength of those variations, and another unitary matrix V star that we're not actually going to use here. And so we've got, the focus here is on the unitary matrix U, because we're looking for the variations. And I can actually reshape them back and plot them as images, and this is what we get. It's a little bit hard to see, especially in the first two ones, but you can kind of see a little bit of difference in the bright and the dark areas. That's where some variation is happening, especially when you get down to like the third image. You can really start to see, okay, there's different shapes going on here. There's different patterns and spatial distributions that we're starting to see. And so what I do is I actually create what is called an eigenspace of the first three images. I take all of my images and plot them onto this eigenspace. And this is what we get. So if we look here, you can see all the MVIs. There's one cluster right here. There's sort of another cluster right here. And you can actually go through and look in these clusters and say, okay, what are these clusters telling us about the spatial dynamics of kelp? Because if kelp were random and not correlated to physical processes, we would expect to see just this big conglomeration or just one big cluster that doesn't actually tell us anything. But because we see different clusters, and not only different clusters, we actually also see outliers, we're able to correlate some of the different spatial variations with specific flights. So we're going to look at that now with the outliers. I'm just going to rotate this space so that we're looking at the first eigenimage plotted against the third eigenimage. And if you focus on the hexagon-shaped dot over there on the right side, you'll see that it plots really high in the first dimension, indicating that it has high correlation with the first eigenimage or the bright pixels in the first eigenimage. So if you look at that first image, you see some of the bright pixels kind of in this bottom left area of the Isla Vista kelp forest, and we would expect to be able to go back and look at flight 2014 line 3 and see kelp there. And the same thing is true for 2010 line 1, which plots really high in the third eigenimage or dimension. We can actually look at this image and say, okay, it has high correlation with this image. So if we go and look at those flights, that's what we see. We see 2010 line 1 is contributing that spatial shape to our space. And 2014 line 3 has some of that kelp that we were expecting to see in the bottom left-hand corner. So we're able to say, this is what kelp looks like, this is how it varies. And not only that, but some of these variations are coming from different flights. I want to draw your attention now to the clouds that we see in the left side of that image, because now we're going to talk about cloud clustering. I've changed the algorithm a little bit. Instead of looking at just the marine vegetation indices, I'm now looking at bands 6 through bands 10 of all of the flights except for 2014 line 3. And you can see from here, we've got a really nice cluster of flights kind of right over here, and then sort of just these outliers or maybe another cluster of flights here. If we take a top-down view onto this space, we get this. And you can actually see that that bottom cluster of flights are flights that contain only kelp. They don't show any clouds. Whereas that top one and the one to the far right are both flights that contain clouds. And so what we can do is run a classification function or scheme on this space to split up the space into bottom, kelp only, and top also includes clouds. Now what we do is we take in flight 2014 line 3 and I project it onto the space to see if the computer or the algorithm is able to classify a new image as kelp only or clouds. And we know that 2014 line 3 has clouds because we just saw it, and the computer plots it right in the clouds cluster. And so it's able to look at this and say, wow, this image has clouds, it's not kelp only. So in conclusion, what do we know? We were able to obtain a basis for the spatial patterns of the kelp forest. We had that average face, plus we were able to pull out the primary modes of variation. We were also able to correlate some of the spatial patterns with certain flights. So like we saw, that flight 2010 line 1 correlated really well with this image. And we were also able to differentiate between kelp and clouds. So we have pretty good results, I think. Where can we go from here? Well, if you've noticed, I've kind of been talking to you about the algorithm and just sort of talking you through it and discussing it a little bit. But I want to go through quantitatively and say, here's the statistics behind the algorithm to show rigorously this is how it works. So I want to kind of get to do that. I want to automate the data manipulation process. I didn't talk about it a whole lot, but it took me half the time that we were here just to move the data around and manipulate it to make it look good for the algorithm. So I want to automate that to make it go faster. I want to look at long-time Landsat images, and not only that, but also consider different spatial resolutions. Landsat, master, DCS, just kind of whatever we can get, and see, is it telling us different spatial patterns at different resolutions? Are we able to see the ENSO variations? And not only ENSO variations, and not only being able to differentiate between, say, ENSO and clouds and kelp, but anything else that an oceanographer or an ecologist could take this algorithm, make a group of something physical that's happening with kelp, run it through the algorithm, and see if the data is able to cluster to give us more insight of how kelp is changing. And lastly, I want to test against already existing processes, because this is really fun math, and I think it's a really cool algorithm, but if it's not better than what's already out there, then it's just sort of like a fun project that sits on my computer. So I want to test against what we already use. And let's not forget to enjoy the rest of our summer break, because that's awesome. I want to say special thank you to Jennifer Broughton and Rafe Kudela for all the encouragement and all the insight and direction, and for making sure that I always had the data that I needed to have. Thank you to Emily and Rick for this awesome opportunity. This awesome program has been fantastic. And for NASA for funding it, for sponsoring it. Everything's been great. Special thank you to Nathan Coots and Steve Brunton, who you guys have no idea who they are, but they were my scientific computing professors who taught me about the SVD and taught me about eigenimages. And this would not have been possible without them. And lastly, thank you to all of my fellow Sarpians, because every single day I've gotten to hang out with you guys and have the time of my life this summer. So thank you for an awesome summer, and thank you for listening to my presentation.